Now we'll move to our next panel, current safety practices of main and short line railroads. I think those who are coming, Pat Brady, Assistant Director of Hazardous Materials for BNSF Railway Company, David Wickersham, the Chief Engineer, Western Region Union Pacific Railroad, Keenan Beard III, Senior Vice President and Chief Operating Officer of the Modesto and Empire Traction Company, and President of the California Short Line Railroad Association, and then David Bucolo, General Manager, Central California Traction Company. Thank you very much, gentlemen.
Mr. Chairman, Juan Acosta on behalf of the BNSF Railway. I just have a witness, Mr. Brady, who has a flight to catch, and due to the late start.
I think that's a great idea. Very good.
If you don't mind, if he leaves at 6, it's not out of disrespect for the chair or the committee.
He is first up anyways. Okay, that'd be great. Very good. Mr. Brady, thank you. And you can, whatever you're comfortable with. And as you know, I apologize for the late hour. We did get a late start, unfortunately, but we can move through it as quickly as you'd like. So, Mr. Brady, thank you.
Thank you. And I appreciate the committee's time. Dave, you gonna? Is there a clicker? I'm gonna grab that for me. So well, let me just clean up a couple things. Again, my name is Patrick Brady. I'm Assistant Director of Hazardous Materials for BNSF Railway. The first slide up there shows a unit crude oil train, and there was some testimony before that said, that these are extraordinary long trains. That is incorrect. This is an average size train, about 5,000 feet long. We operate trains in excess of 10,000 feet from LA to Chicago intermodal trains. We have heavier trains. So this is an average size train as far as length and as far as weight. And Dave, it's not working. There we go. Okay, so what I'm going to cover in my presentation, again, I'm with our hazmat group. I'm going to talk a little bit about where we are from a safety standpoint and really how we got there, where we are today. So if you look at this first slide, this is U.S. railroads. So this is all the railroads, BNSF, Union Pacific, the Eastern carriers. And you can see that between 1980 and 2013, that accident, employee injury, and grade crossing incidents have fell over 80% over that period of time. And 2013 was our safest year on record. And these are BNSF specific statistics. And this shows reportable rail equipment accidents. And this is by per million train miles. And you can see 2013, again, was the safest year on record for the BNSF. And you heard testimony earlier that 99.997% of hazardous materials go from origin to destination without having a release. 2013, again, was BNSF had the fewest number of mainline derailments in company history. And accident rates have declined 91% since 1980. So the question is, how did we get there? And you can really look at it in 3 separate buckets. So those buckets are investment, which Mr. King talked about, employee training and compliance. We'll talk a little bit about behavior-based safety, and then inspection and infrastructure, which this committee has already asked questions about. So here's our capital investment, 2000 through 2014. Our projected capital in 2014 is $5 billion. You can see the distribution of that capital in replacement. That would be the infrastructure replacement, expansion, PTC, locomotive, and other rail equipment. One of the things that is very important to realize, let me go one more slide, is that we are a very safe but unforgiving industry. Meaning in a lot of industries, if you make a poor decision, you may get a bruise, you may get a small cut on your finger. But in the railroad environment, we operate very heavy equipment, and it could be a critical decision. So when you look at it, we have a culture of compliance, which means that we require 100% rules compliance 100% of the time. And we look at some of our safety, critical behavior safety focuses. You'll see things like deadly decisions, critical decisions, safety absolutes, because in the end, it may mean a employee's life or a limb if they choose the wrong behavior. So We have about 40,000 employees operating in 32,500 miles of track. So a lot of these employees spend a good chunk of their day without a direct supervisor looking over exactly what they're doing. So one of the things that we're looking at, we understand that in behavior-based safety, that an employee makes decisions every day. And some of those are the right decisions, some of them are the wrong decisions. And we can't have a supervisor looking after exactly what they're doing 100% of the time. So we have a program called Approaching Other People About Safety, meaning that a peer-to-peer or even peer-to-supervisor would watch the employee's behavior, and if they do something that is not within rules compliance or something that could get that employee hurt or killed, that it is the responsibility of that employee to approach their peer or even their supervisor to make sure that they're doing the right thing and they understand that that behavior will not be tolerated at the BNSF. And because of that, we feel that it is driving down our injury rate. You can see the BNSF's injury rate per 200,000 employee man-hours based on the rail transportation industry, mining, heavy engineering, construction, truck transportation. So again, very safe, but somewhat unforgiving. One of the other things that we look at is our infrastructure. So when you look at the cause of derailments, you have track, you have equipment, and you can have human factors. So this is the track, and my colleague from the Union Pacific is going to spend a lot more time on track and bridge inspection. But we look at risk-based inspection, so key trains or key routes, which are a specific amount of hazmat traffic over a 12-month time period, that those routes get inspected either 4 times a week, or on the busiest main lines will be inspected daily. We have other inspections using state-of-the-art technology to detect internal and external defects in the rail. Also looking at weather, severe weather that could cause a derailment, or earthquake inspections. Here's just a couple pictures. Again, my colleague from Union Pacific will go into greater detail on the different type of track inspections. The other thing that we look at is rail car defect technology. Again, cause of derailment could be the components of a rail car itself, roller bearings, wheels. So we utilize the latest in technology to detect those flaws before the derailment actually occurs. There's also testimony on positive train control. BNSF has spent a great amount of capital on PTC, and we are working towards meeting the federal mandate on PTC. So the other thing that we talked about, so we talked about operations. The other testimony or questions were on equipment and the characteristics of the crude oil. After the Quebec incident that happened in July of 2013, FRA put out an emergency order to ensure that something like that could not happen in the United States. And from that, the railroads changed how we define a key train, which now is defined as 5 loads of toxic or poison inhalation hazards, or 20 cars of any other hazardous material in a train would consider it a key train. When you have a key train, that those trains cannot be left unattended. And if any time an emergency responder, fire department was around the train, it needs to be resecured by a railroad employee. So for decades, we have had self-imposed best practices for derailment prevention. Some of these things, again, are the key train definitions. When you have a key train, again, 1 car of toxic or poison inhalation hazard, 20 cars of any other hazardous material, that we require special tracking, 50 miles an hour speed restrictions on those, and special handling of wayside detection, such as a failed bearing detector. On Friday of last week, U.S. Secretary of Transportation Fox put out a agreement that the FRA has with the railroads that increase track inspections on crude routes, required speed restrictions of 40 miles per hour on high-threat urban areas, decrease distancing of rail flood or hot bearing detectors, using our routing analysis for the most safe and secure route, and working with emergency responders to ensure that emergency responders are informed and trained in the event of emergency. Some other testimony was on the rail car. It's important for the community to understand that as a common carrier, railroads are required, as long as our customers properly describe and package the material properly, we have to accept them in transportation. The legacy DOT 111 tank car is still a allowed specification package by the Department of Transportation, so it is being used today for crude oil. We are pushing for a new design. The interim design is what we call the CPC 1232 car, which has thicker metals, thermal protection, and the railroads have pushed for even a higher level of tank car, which has 9/16" carbon steel and very similar in design to a tank car that would be used to transport liquefied gases like propane. We are pushing to phase out the legacy DOT 111 tank cars and require retrofit to those cars that stay in service. In case of to allow more time for my colleagues, do you want to ask questions of me specifically now, or wait till
Are you
the end?
finished, Mr. Brady?
Yeah, sure.
Oh, okay, very good. Thank you, and I want to welcome Senator DeSaulnier to the hearing this afternoon. I just had one question. You talked about, obviously, because of the reduction in incidents over the last few years, you mentioned how you got there. My question would be, looking at the increased volume as we move forward based on the projections and based on what we're seeing today, how are you going to stay there?
So when we look at things like wayside detections, when we look at things like track inspection, when we look at things like employee training, it's all based on risk. So as your volumes increase, your risk of a derailment would increase, so therefore you would increase the inspections, you increase the distances or decrease the distances between wayside detection. So it's all based on the risk of the track, meaning that if you had a track that saw one train every week, the probability of that train derailing is very low. But if you ran 40 trains a day, the probability of that one of those trains being involved in derailment is higher. So your risk reduction methods are used on risk or the volume of materials.
And it would be the same with the size of the trains as well, the length, the weight, and all the other things. Is that taken into consideration?
Correct, yes.
Okay, very good. Thank you. Now, I do have questions on bridges. Should I ask? I'll ask you on the bridges. All right, that's very good. So, Senator DeSaulnier, no questions there? Mr. Brady, thank you. Appreciate it. And do we have copies of those slides available for somewhere? I don't know.
Yes.
Okay, very good. Thank you very much. Appreciate it, Mr. Brady. Now you have a plane to catch. You got a couple minutes left. All right, very good. Thank you. Mr. Wickersham, is that, am I correct in that?
Yeah, that's correct.
Chief Engineer, Western Region, Union Pacific Railroad.
Yes, can you hear me okay?
I can hear you fine.
All right.
Thank you. Welcome.
So my name's David Wickersham. I'm your Chief Engineer for the Western Region of the Union Pacific Railroad. I'm very honored to be here today. I've got 20 slides. I'm going to try and get through them real quick.
Yes.
Okay. My mission and my team's mission is to go home safe every day and keep the trains on the track. That's what we're all about. Our Western region is headquartered here in Sacramento, actually in Roseville. I'm a citizen of California. I live in Roseville. My house is 1,000 feet from the main line. So when I wake up in the morning, when I go to bed at night, I think about keeping trains on the track. So with that in mind, let's see. Here's, see if I get this right. Oh, that's a great picture of the Tehachapi Loop, which is just south of Bakersfield. It's a historic national monument, and it's joint trackage. BN trains operate over that track as well as UP trains. This is the Union Pacific Railroad route structure. It's very similar to UP. UP is our direct competitor. Routes into California are that Sunset route, basically from New Orleans and Memphis into Southern California. That's principally serves the ports of LA and Long Beach. The I-5 route, which basically parallels Interstate 5 that comes down from Seattle to Portland and on down to Los Angeles. And then our Central Corridor, which is the original Central Pacific Railroad and the Union Pacific Railroad that started right here in Sacramento across the interstate here. We have 32,000 miles in our route structure. In California, so here are the routes in California. So it's basically 10% of our system mileage. We have our I-5 route from State Line up there at near Klamath Falls. It comes down through Dunsmuir down into Sacramento. We got the Feather River route, which is the original Western Pacific route that parallels through the Feather River Canyon. We've got the Donner Pass route that was built in 1863 from Sacramento over. Principally, it's still the same alignment that was built in 1863. We have our San Joaquin Valley line, our coastline, and our Sunset route from Yuma into Los Angeles. This is how we're perceived as maintaining our railroad. This is what we all read in our history books. This is actually the Central Pacific Railroad just out of Reno, heading towards Salt Lake City. Everything was done by hand and by mules. This is how we do it today. So up in the upper left-hand corner is a cross-section of our railroad. And it's very similar to an interstate highway. So instead of putting your ties right onto earth there, we've got that compacted subgrade. We have sub-ballast. We have 12 inches of ballast, and we have our cross tie. And the graphic on the right shows what a rail section looked like in 1863. It's measured by pounds per yard. That was 62 pounds per yard. And today our standard is 141 pounds on our principal routes, on our Donner Pass route, and everywhere else 136 pounds. And it's the same standard rail section that the BN uses. We share a lot of technology together, and we share a lot of best practices together. This is how we do it. Our track inspection, I'm going to talk about track inspection, bridge inspection, and signal inspection. So this is how we do it in California. So we have 43 full-time dedicated track inspectors working within California. They go through the same training that an FRA inspector has. It's a 5-day course and before we put them out on the track. They're evaluated monthly by their managers, and they do annual training, and then they do on-the-job training. And we have a Bible, we call it our Track Maintenance Field Handbook. It's quite a lot thicker than the minimum FRA track safety standards. And what we preach is compliance with our policy, not the minimum FRA standards. There's 17 managers of track maintenance that are headquartered in California. They supervise 480 track employees that are maintaining the track on a day-to-day basis. The principal job that a track inspector does, that's his tool right there, that picture. That's a high rail pickup. And when we say high rail, there's rail wheels on the front, there's rail wheels on the back. And you've probably seen them on the track, you've seen them driving down the highway and take a second look. But you can line up that inspection vehicle on a road crossing and set your rail wheels down on the front and the back and lock them in place. The tires are set up so they're directly over the rail, and then all he has to do is step on the gas. Doesn't have to steer, obviously. So that's the principal inspection. When a FRA inspector or a PUC inspector comes out on our property, they'll hook up with one of our guys here, one of our track inspection teams. Our managers also have these vehicles, and they'll go with either one of our managers or our track inspectors, and they'll cover that particular territory that you can cover in a day. What they're looking for is anything visually that a human eye can see. So they're looking for a broken rail. They'll actually feel that. But they're looking for maybe a little warp in the track or a surface condition. And when they see something that doesn't look right or doesn't quite feel right, they'll stop, back up, and then they have track tools that can measure exactly what the cross level is, exactly what the problem might be, something that they can see. And then also we do special inspections. So whenever it rains, for example, we will escort trains with one of these vehicles. We'll be about 3 miles ahead of them through the Feather River Canyon, where we know we have rocks come down. If there's an earthquake, we have procedures on the magnitude of the earthquake, how far we inspect. So, for example, if it's an earthquake over 6, then all trains are stopped within 100 miles, and then we get track patrols out to look at the track to see what damage we have. Additionally to those inspections, the next 2 inspections I'm going to talk about are really key tools, and they're really cool because it's using advanced technology to do what the human eye can't see. We have 2 state-of-the-art track evaluation cars or track geometry cars. They're about $10 million a piece. And basically what they are is a self-propelled vehicle, and we can tow them with a locomotive too. But they have onboard computers. They have sensors, a whole array of sensors underneath the car. And as you're going at track speed up to 70 miles per hour, it's measuring things like the distance between the rails, the cross level of the track, the alignment of the track. All these measurements are inputted into the computer immediately. They're cross-referenced with UP standards and FRA standards, and immediately what prints out, if there's an exception, it'll say, there's an exception here and you need to drop the speed of your track. Additionally, some stuff that we do that's really good, it's data collection. This is what we're all about. For example, as there's one sensor that has lasers that measure the cross-section of a rail, and it tells you how much wear is in the rail. And we use this data to tell us where we're going to lay our curve rail every year. So that was a question about how are we going to maintain the track moving forward. So track wears out because you have a steel wheel on a steel rail, and the track wears out as a result of tonnage. So if tonnage is increased, then the wear increases, and then we catch it with this machine, and we know when we have to replace our rail. It also measures clearances in tunnels, clearances in bridges. It even measures the clearance between 2 tracks if we have 2 mainline tracks. And it also takes a video of the track. So I can go in to our computer system, and I can look at, in 1 mile bytes, the last run that this geometry car made. And I can get a video clip of what that track looks like sitting in my office. So it's really cool technology. Now moving on, here's another interesting technology. It's really been around for 30 years, but each year it keeps getting better and better and better. This is our rail detection system. So what we're looking for here is an internal flaw in the rail before it breaks out in the rail head and could cause a derailment. So basically how it works is it sends the same type of a vehicle that pickup truck was. You can drive it down the highway. You can set it on a road crossing and go down the track. It actually sends a sound wave through the rail. And it's got a computer on the car, and based on how that sound wave behaves, it will tell you what type of flaw is in the rail. And there's about 15 different types of flaws that it can find. So the computer's kind of programmed, okay, if the sound wave does this, this is a detail fracture. That's in the lower left-hand picture. That's a detail fracture. And it's caused by a small, maybe speck of dirt when the rail was made. And over time and tonnage, there's a fatigue defect develops. Similar to that. So our goal is to find it before it breaks out in the railhead. We have 4 of these cars dedicated to California. And I keep winning the battle with my Omaha headquarters. We always get the latest technology out here in California. So that's pretty cool. Now I said track wears out. So the ties wear out, the rail wears out. So what we do with wood ties is we'd like to come in every certain cycle and replace 25% of your railroad ties. You don't want all your ties going bad at the same time. That's a machine there we call a tie injector. It's taking old ties out and installing new ties. I can tell you from my 20 years with SP, and I really want to thank Paul King for his comments, and I neglected to thank Dr. Lindsay for her report. I think her report was spot on. I didn't see any errors in it. I think she did a really excellent job. But in my SP days, the amount of ties and rail we laid in California in a 5-year period was about half those. So that's you really want to work for a railroad that makes money, and our railroad gets it. I know the BN gets it. Our prime business is running trains safely. That's how we make our money, and the way you make your money is to put the money you earn back in the track structure and make sure it's in top condition. I have to agree with Paul that really our riskiest areas in California are mountain grades. And the right thing to do is to make it as strong as possible. And the strongest track that we can come up today is a concrete tie railroad. It costs a lot more. It's about $120 to install a wood tie. It's about $300 to install a concrete tie. And what the UP has done, right after they bought the Western Pacific, about 10 years later, they put concrete ties in the Feather River Canyon. Since the merger with SP, they started and put concrete ties in the Tehachapi Mountains. Then they went north of Dunsmuir and south of Dunsmuir. These are all the mountain grades in California. We are 33% complete Donner Pass. We're taking it in bites. We got another 25 to 30 miles planned next year. And the Sunset Route is 50% complete. And the BN is doing the same thing with their critical areas. That's a picture of our track lane machine on the lower left. It operates about 2 miles per hour. You got wood track in front of it, and you got concrete tie track behind it. Now to our bridges. Okay, so there are 3,100 bridges in California. That compares to about 20,000 on our system. We have 56 miles worth of bridges in California, 20 miles for concrete bridges, 26 miles are steel bridges, 10 miles are timber bridges. So if you remember the bridge fire right here on the American River a few years back, I responded to that. Our guys from Omaha came out, rebuilt that bridge in 11 days. That was the timber approach to the steel truss span. So most of our timber bridges are small structures that we're replacing with concrete and steel. We have 28 miles of tunnels in California. We have 7,300 culverts over a 4-foot diameter. This is our goal. You can't have, our bridges are like our factory. If we lose a bridge, we're not producing anything. We're not running trains. They are critical to us. So our job is to ensure the structural integrity of those bridges. We must comply with FRA bridge safety standards. In California, we're inspecting our bridges every year, every 1 to 3 years. And this is how we're set up. We have 6 two-person full-time teams working within California. We call this truck a snooper truck. So here's another truck that can go down the highway and on the track, and it's got a person lift or person cage. If you look at that picture, you can see how we can look underneath the structure and on the top part of the superstructure. This is our Donner Pass line. We have 2 managers of bridge maintenance headquartered in California, and we have one I omitted it here, but we do have one manager of bridge inspection. All these inspectors, they work for our registered professional engineers out of our headquarters in Omaha. They work directly for them. So the cool thing about that is they call the bridge defects as they are. We have a very complicated bridge book and bridge inspection process that we've shared with Paul King's team. We brought him out and showed him how we do it. We've shared with them those bridge inspection books, but we'd be very willing to share that with your staff to show you how we rate our bridges based on the maintenance issues on those bridges. And that drives what bridges we replace. So this is what UP has done in the last 5 years in California. We've replaced 70 bridges. Our signal inspection program in California, we have 218 signal maintenance employees, and every one of them is involved in some type of inspection. So they're responsible to maintain the wayside signals and the grade crossing devices. So these signal maintainers that I have there, there's 161 of them, every month, for example, they have to inspect that grade crossing device to make sure it's working properly. Our signal system obviously governs our wayside signal system to move trains, but it also provides for broken rail protection. This is a little update on our positive train control. It's pretty similar to where the BN is. Everything in green on the signal side has been turned over to operations. So our old signal system with our old relays is not compatible with PTC. We had to basically change out every power switch machine cabin with new electronics so it's compatible with PTC. This was our big expense. So we've been flat out constructing, upgrading our signal system since the legislation was passed. I'm going to do my best to give you PTC 101 here, but using GPS, there's a simulation of a locomotive and a signal down below. That's our dispatching center in Omaha. There's a computer in the back room, and think of a satellite up there that basically all this is interconnected. We have all this information on the track that's GPSed. Every switch is GPSed, every signal is GPSed, every indication that that train needs to know is located. So what happens, so say the train crew is not paying attention to signals, wayside signals, and the system will override anything that train crew's doing and stop the train. So say there's another train coming in the other direction, this train has to stop. And the crew, for some reason, does not recognize that. So the system takes over. There's a braking curve and there's a warning curve. And it will take over and it will stop the train before it gets to the signal. It's a pretty cool graphic, but it's a overriding. It's not this. It's tied into the signal system. It's a separate system completely. This is my last slide, and this is a real key component of reducing derailments. And the BN has done this as well. We share all the same technology, but these are trackside detectors that basically look for something in a rail car to prevent derailments. And for example, I'll just give you that top one there. That's a bearing temperature scanner. We commonly refer to that as a hot box detector. So if a wheel gets hot, it can burn off and cause a derailment. So it's temperature. It's a high temperature that will start heating up before it actually fails. So every 20 to 25 miles, we have one of these detectors. And as the train's going over, it measures heat on each wheel. And when there's a hot one, that's a temperature differential. So it recognizes it. It activates over the radio that's in that wayside cabin, broadcasts over the radio, stop your train, axle 142. It's actually counting axles. So that the crew stops, and the conductor has to get out and walk back. He's counting 142 axles. And he has a little tempo stick that melts at certain temperatures, and he can verify exactly what car it is. If he miscounts, then the rule requires him to count 10 each way to find it. But we just keep getting more and more technology. We have about 12 wheel impact detectors. So if we have a flat wheel that's banging on the rail and making an impact, it tells us that we've got a flat wheel and we've got to set that car out. This stuff keeps changing every 3-4 years. We keep getting better technology. And I kind of rushed through it, and I wish I had more time to go into detail on how we do it. But it's pretty exciting stuff.
It's very, very exciting, and looks like you're paying attention to what needs to be done, at least from what I can see there. Getting back to the bridges and the issue of, and I'm just referring to the CPUC's report of last November, and you probably heard my question earlier about paperwork, documentation, and history. I mean, from this, it looks like this isn't an issue, at least based on that. Do you see that or feel that your bridge inspections, analysis, and record keeping is is adequate, especially going back to the question,
I'd
Brady,
say-
with the need, the future volume that you'll be carrying on these bridges?
I would say it's very robust. Very robust. It's been a while since I took calculus. And I just did a little math. So I was trying to figure out how much 158 million barrels are. So we put 700 barrels in one of these tank cars, and that's 227,000 cars. And then I figure if we haul, if a train is 100 cars per train, which I think it might be 50, but 100 cars per train is 2,271 trains. And 2,271 trains, and we're 300. We only stop moving trains on Christmas Day. We're open for business every other day. So that works out to 6.4 trains per day between our two railroads. So, I'm very confident. I mean, our bridges are all rated at E60 or above on our main lines. The amount of weight of these cars are similar to our, as Paul King said, similar to our unit grain trains and some of our unit coal trains that we run in California. I don't see the issue here.
Do you see the bridges in terms of aging infrastructure of them, is that presenting a problem, or your continuous inspections and repairs and recalibrating them, however, do you feel that's adequate?
I feel it's adequate. We do have a lot of old structures. So, for example, the Martinez Bridge that goes over the San Francisco Bay, the Carquinez Straits. It was built, I think, in the 1910s. We're looking at that bridge 3 times a year. We have outside contractor, registered civil engineers that come out, and they spend 2 weeks crawling all over that structure to make sure there's no issues. And then they've been doing it every 3 to 5 years, as long as I can remember. And we have a maintenance program that they recommend, and they update it every time they inspect it. So I was told, that all our original railroad structures were all built for steam locomotives, and that drive wheel of a steam locomotive, if you've ever gone over in the California Rail Museum, highly recommend it. But look at that cab forward steam locomotive, and the size of that wheel and the weight of that steam locomotive is far in excess of what loading that we put on the track today per wheel. So we have 6-axle locomotives. We spread that weight out over an extra axle. Our point load per wheel is much less than that drive wheel of that steam locomotive, and that's been in our favor.
And are you making infrastructure investments in those bridges, not just from repairing, but as you're looking at the Martinez Bridge, for example, in terms of replacing that at some point in time?
Quite a few components of that structure have been updated over the years, especially the lift mechanisms.
You mentioned in positive train control, it's my understanding that short line operators are not required to have positive train control. However, they sometimes will ride on and be on main lines.
That's correct.
Create a problem?
That's one of the challenges. But
thank you, Mr. Brady.
Basically, what that means is their locomotive has to be compatible with our locomotives that we run. So in order for them to come out onto our main line, their locomotive has to be similar to what our locomotive is.
Very good.
And we're working through that.
Mr. Wickersham, thank you very much. Appreciate your testimony and the information today. Very nice. Thank you.
Thank you. Thanks for allowing me to speak with you.
Thank you very much. Really appreciate it. Very thorough.